Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I hope all of you are doing well. Either you are at home or you are at the college. So for today we are going to continue our lecture on the third chapter. Right? We have completed the shaft power cycle, and for today we are going to look at the new topic. Okay, the topic for today's lecture is on gas turbine cycles for aircraft propulsion. So we have already looked at the shaft power cycle, so many configurations and some examples on efficiency and cycle calculations. So for today and the lecture right afterwards, we are going to look at the criteria of performance, and later we are going to go into the intake and propelling nozzle efficiencies. We are going to go through simple turbojet cycle, turbofan engine, turboprop engine, and thrust augmentation. So for this particular lecture, we will focus on the criteria of performance. So in terms of the learning outcomes, at the end of this session, you should be able to explain the difference between performance of gas turbine cycle compared to the shaft power cycle, right? And then basically you're going to be able to describe the criteria of performance of gas turbine engine, and also be able to compare the propulsive efficiency, energy conversion efficiency, and the overall efficiency. Right. In terms of the aircraft gas turbine cycle, it differs from shaft power cycle, right? So we are going to look into what are the differences. The first one, the useful power output is in the form of thrust, and the second one is that the effect of forward speed and altitude on the performance. These are the two differences between a typical gas turbine cycle compared to shaft power cycles. Right. The designer of aircraft engines must first recognize the differing requirements either during takeoff, during climb, cruise, as well as maneuvering. Right. So you as a designer, aircraft engine designer, you must take into consideration of these conditions. And engines for long-range aircraft, okay, when you design a long-range aircraft, it requires low specific fuel consumption at the cruise speed as well as the altitude, while the thrust level may be determined either by the takeoff thrust on the hottest day likely to be encountered or by the thrust required at the top climb. Right? Those are the considerations you must take into account whenever you want to design an aircraft engine. In terms of the criteria of performance, right? If we look here in figure 3.1, a typical propulsive duct, okay? So the relative to the engine, okay, we have the air enters the intake with a velocity of CA, right? So the air coming into the engine, right? Imagine this is just a schematic of the power unit, the propulsive duct, and opposite, which is equal and opposite to the forward speed of the aircraft. So the aircraft is moving this way, okay? Basically, this is aircraft direction. Okay, and the air going into the propulsive duct, right, in the opposite direction. Okay. And the power unit accelerates the air so that it leaves with the jet velocity of Cj. Okay, so we have the air coming out the propulsive duct, which is denoted by Cj. Okay, Ca incoming air, A for ambient, J for jet. Right, so we have the ambient pressure as well as the jet pressure, and then the ambient pressure also acting on the power unit. That's are the typical configuration when we want to look into the criteria of performance for aircraft engine. For simplicity, we assume that the mass flow M, okay, we have the mass flow which is denoted by M or M dot. Okay, for some other text they use M dot, but for simplicity, for this our lecture, we are going to use M, where we assume that the fuel flow is negligible. So basically the MF is negligible in our calculation, and thus the net thrust F, the thrust, this is the thrust, okay, is equal to the rate of change of momentum. Okay, this has been discussed quite lengthy when we go through the subject of propulsion. So we have equation 3.1, and MCJ, okay, this particular component, okay, MCJ is called the gross momentum thrust, and MCA is the intake momentum drag. Okay, and then when the exhaust gases are not expanded completely, it is not fully expanded to the atmospheric, basically to PA. So we have the basically the air coming out from the propulsive duct is not expanded to PA completely, it's slightly higher. The pressure PJ, the pressure at the jet in the plane of the exit will be greater than the PA. So basically, PJ will be greater than PA, right? And there will be an additional pressure thrust exerted over the jet exit area, okay, which is AJ equal to the AJ time the difference between PJ minus PA, right? So this is the extra pressure thrust exerted over the jet exit area. And the net thrust is the sum of the momentum thrust as well as the pressure thrust, namely as this equation. So this is the complete jet engine equation as denoted by 3.2. Okay, earlier 3.1 is just simply assuming that the air exhaust gas are fully expanded to atmospheric pressure. And the thrust can be obtained by designing the engine to produce either having a high velocity jet, okay, it can be having a high velocity jet of a small mass flow, or a velocity jet of a high mass flow. And the question arises as to what is the most efficient combination of these two variables, whether you want to have a high velocity jet coming out from the propulsive duct of a small mass flow, or a high velocity jet with a high mass flow. So which one is better? Let us look at the propulsive efficiency or the propulsion efficiency zeta P, and that can be defined as the ratio of the useful propulsive energy or the thrust power. And we have the F times the CA, and the thrust times the air coming into the propulsive jet, and then to the sum of that energy and the unused kinetic energy of the jet. So the latter is the kinetic energy of the jet relative to the earth, namely as this expression. So we have the mass flow times the difference between the jet minus the incoming air to the squared divided by 2, and thus the equation 3.3 for the propulsion efficiency can be written, right? And this zeta P, the propulsion efficiency, also called as the fruit efficiency. And from equation 3.1, the earlier equation, as well as 3.3, it is evident that the thrust is a maximum when the incoming air velocity equal to 0. In other words, it's under static conditions. but the propulsive efficiency is also zero. So you do not have a propulsion efficiency there. And the propulsion efficiency is also maximum. Okay, it will become maximum when the exhaust jet over the incoming air velocity equal to 1. But then the thrust will be 0. All right. So we may conclude that although the exhaust velocity Cj must be greater than Ca, the difference should not be too great. So as an engine designer, you have to be able to see what are the best combination for your engine. So this is a family of air breathing engine. So we have the piston engine, the turboprop engine, turbofan engine, turbojet, as well as the ramjet. These are the air breathing engine family. And it is decreasing mass flow. So what do we mean by that? The piston engine has less mass flow compared to the ramjet engine. And it is at the increasing jet velocity. So from A, B, C, D to E, the higher will be the jet velocity. Okay. So basically, you are talking about the M and the CJ over here, right? And this particular figure, figure 3.3, showing the flight regimes. We have the y-axis denoted by the altitude from 0 to 20,000 meter, and the x-axis noted by the Mach number from 0 to 3. Okay, so we have the what being shown here is the flight regime found to be suitable for broad categories of power plant installed in a civil aircraft. So let's say you are the engine manufacturer, and also you are the other person is the airline that would like to buy a new type of aircraft, and you have to decide what are the suitability of your engine. So for example, like the turboprop is suitable at a low altitude with a low speed, less than 0.5 to 0.7 probably, and a turbofan up to 10,000 meters. Okay, and then a turbojet, which is probably having a higher altitude and a higher Mach number. So the propulsion efficiency is a measure of the effectiveness with which the propulsive duct is being used for the propelling the aircraft. And it is not the efficiency of the energy conversion within the power plant itself, meaning that it is not the energy efficiency for the combustion process energy. Okay, we have the combustion and to be converted into the kinetic energy at the turbine. So the rate of energy supply in the fuel may be regarded as this expression. So we have the MF, okay, where MF is the fuel mass flow, okay, and this is converted into potential kinetic energy for propulsion. Okay, we have the same expression for the kinetic energy for propulsion together with unusable enthalpy in the jet, right, which is being expressed there, and where the energy efficiency, okay, is defined as this expression 3.4. So we have the component of the fuel, okay, the mass flow of the fuel, okay, the amount of heat being transferred, and the element of the kinetic energy, right? And the overall efficiency, or called the zeta O, is the ratio of the useful work done in overcoming the drag to the energy in the fuel supply. So we can write the overall efficiency as the following. Okay, so we have the components of the thrust, the incoming air, the mass of the fuel, as well as the energy that involved. So the denominator of equation 3.3, okay, of a zeta p, okay, is equal to the numerator of equation 3.4. Hence, equation 3.6 can be written as shown here, right? So we have this expression, and efficiency of the aircraft power plant is linked to the aircraft speed, right? So we can say that the overall efficiency of the aircraft engine is also linked to the aircraft speed. The overall efficiency is given in equation 3.5, can be written as follows, where we now introduce the specific fuel consumption in the equation. Another important parameter is the specific thrust. Okay, we have the Fs, namely the thrust per unit mass flow of air. So the unit is basically Newton second per kilogram. And this provides an indication of the relative size of engines producing the same thrust, because the dimensions of the engine are primarily determined by the airflow. And the specific fuel consumption and the specific thrust are related by equation 3.8, which is specific fuel consumption equal to the F over Fs. So considering the cycle performance at altitude, the ambient pressure and the temperature varies with height above the sea level. So according to the International Standard Atmosphere, or known as the ISA, so we have the ISA, correspond to average values at middling latitudes and yields a temperature decreasing by about 3.2 Kelvin for every 500 meter of altitude, up to 11,000 meter. So from 500 meter to 11,000 meter, there will be a temperature decrease of 3.2 Kelvin, and which is constant at 216.6 Kelvin until 20,000 meter, right? So that's what the data from International Standard Atmosphere has already stated. Okay, once the temperature is fixed, the variation of pressure follows according to the laws of the hydrostatics. Okay, this is I believe in the propulsion subject you have a few examples for calculating the performance of the gas turbine engine. You have a different altitude, you get a different efficiency for the engine. So for high subsonic and supersonic aircraft, okay, at a higher Mach number, it is more appropriate to use Mach number rather than meter per second for the aircraft speed, because the drag is more of a function of the former, meaning that as the function of the speed of the aircraft. So it must be remembered that for a given speed in meter per second, the Mach number will rise with altitude up to 11,000 meters, and because the temperature is falling before it is fixed. And looking at this chart, a plot of the Mach number versus the incoming air, okay, the speed of the air for sea level and at 11,000 meters. And this is obtained from the International Standard Atmosphere data, and the Mach number is equal to the speed of air divided by the acceleration. So where air is the sonic velocity, is written here. So as we can see here, as the Mach number increases, right, it is also increases with the speed of the aircraft. So, but at sea level is this line for the 11,000 meter. It is slightly higher. Okay, right. So that is the first part of our sharing session for today. We have looked at the criteria of performance. Later, at the second part of the lecture, we will discuss on the intake efficiencies as well as the propelling nozzle efficiencies.